This Nightsearcher Trio LED searchlight has seen better days. As far as I know, the battery stopped charging for some reason, and at some point someone removed the battery and powered this from different power supply through the battery cables. Unfortunately, the voltage was way too high and the magic smoke was released. This video is kind of a project log of me fixing and upgrading this with parts that I already have. I try to include some parts of each step of this process to demonstrate how this kind of a project usually evolves. If I had decided to replace the internals, I would have ordered the PCB from the sponsor of this video, PCBWay.com. PCBs as large as 10 cm by 10 cm cost just $5 plus shipping. That's for 10 pieces of good quality two-sided PCBs. If your project requires 3D printed or CNC milled parts, or maybe some electronics modules, you can get them from PCBWay.com as well. There's no way I could have made this stainless steel key without their metal 3D printing service. For all your prototyping needs, go check out PCBWay.com for up-to-date information on their services and pricing. The original battery is 6V 4Ah SLA battery. My goal is to repair this light and also do a lithium conversion, so this would use handful of 18650 cells instead of that lead acid battery. The 6V of original SLA battery is about the same as an empty 2S lithium pack, but also significantly higher than full 1S pack. Either way, I would need to make some modifications to the light, so I will use 1S pack and boost converter for the LEDs. It's easier to manage and difference in cell capacity isn't as big of a problem. But first I need to figure out what that too high voltage fried, because something definitely broke as the magic smoke escaped. On this LED module, or the PCB behind the LEDs, there's clearly a broken transistor and two current limiting resistors seem to have heated up as well. They are 15 ohm each and they are in parallel, so that makes 7.5 ohms. So if this gets full battery voltage of about 6.5 volts from charged SLA battery, LED's forward voltage is 3.6 volts and maybe 0.2 volts collector to emitter voltage drop from the transistor. The LED current will be 2.7 volts divided by 7.5 ohms or about 360 milliamps. That is the max limit and I'll probably modify this for slightly lower current. Behind the LED module there's plastic divider, which is clearly from design that used older style bulb as it has place where the base or holder would go. It makes sense for a manufacturer to use same parts in different versions or generations. It saves in design and manufacturing and also simplifies inventory. This divider is held in place with screws. It probably is also holding the battery in place. Once that part is removed, I can see the battery and the PCB. The battery is dead, almost 0 volts according to the previous owner, and it's here only for reference. The spade connectors have locking notches on them. I'll use this spike from O-ring toolset to push the lock down while pulling the female connector off. Some of the spade connectors can be disconnected with force, but it may ruin the connector. And indeed, the battery is 6V 4Ah SLA battery. Not that I would be buying a new one, but this could be used to design case for 18650 cells in the future. Before I can take a closer look at PCB, I need to desolder the dual color LED. Its legs go through the plastic case and PCB can't slide out before that LED is removed. Now that the LED has been removed, PCB can slide out easily. The button and another LED have longer wires and they don't need to be removed. On this PCB, at least this one transistor is broken. This is so simple circuit I will draw the schematic and try to see how this was supposed to work. I checked the part number and that 8-pin chip on the right is charging IC. It is quite clear that the right part of the board is charging and left is for switch toggle function. The DC input jacks positive, ground and also the battery is positive are only 3 connections between right side and left side of the board, so it's easy to see which parts are related to which function. There's visibly broken part on the power switch section, which is why I'll only draw the schematic for that section, at least for now. Okay, this is what I came up with. I did not design this circuit, this is only my understanding of this circuit on the PCB. First of all, battery positive and LED modulus positive are tied together, and the LED modulus negative is connected to ground or battery negative through the N-channel MOSFET. So like I guessed previously, the LED module does see the full battery voltage when turned on. Before we go to the power toggle section, this small addition is what makes the emergency light function that turns the LED off when charger is connected but turns it on during power outage. When V in, the voltage on the DC jack, is high enough, the NPN transistor pulls the MOSFET gate to ground. Without charger connected, the output of toggle circuit controls the gate of the MOSFET. There is also an indicator LED connected to the output of that toggle circuit. At first, neither of these transistors is conducting. NPN has pull-down resistor and PNP has pull-up resistor. The capacitor charges to battery voltage through the resistors R4, R12 and R16. When that has charged and the user presses the button, NPN transistor base is pulled high and it conducts, pulling the PNP transistor base down, making it conduct as well. The NPN also discharges the capacitor. PNP conducting will turn the output on and also supply current to base of the NPN through 2 Zener diodes and 1 regular diode. When battery voltage is low enough, voltage drop of these diodes is so high, resulting output won't keep the NPN conducting and circuit will turn off. That's the low battery protection. But when the battery voltage is higher, little bit of current passes to the base of the NPN and keeps it conducting. I can already see why this circuit fried with too large voltage on the battery terminals. There isn't a current limiting resistor in series with these diodes. I don't know the exact values of these Zeners, but they probably were chosen such way that they won't fully break down even with full battery. While one could think Zener diodes just drop voltage by fixed amount, it actually does conduct a little bit even on lower voltages. But in this case someone supplied too high voltage. Let's say these Zeners were for example 3 volt each. So the nominal voltage drop over them, the regular diode and the base emitter of the NPN transistor is about 7.4 in total. What if this was supplied with 12 volts? The current going through these diodes and base of the transistor is 12 volts minus 7.4 volts divided by resistance. And as there is no resistor, the resistance is close to 0 and thus the current will be huge. That has probably fried at least the PNP that has visible marks on it, and also these diodes and maybe the NPN as well. Before I start fixing things on the PCB, I need to test the LED module to see if the LEDs are okay. I have removed the blown transistor and replaced the burned resistors with new ones that give me a desired current when powered with 5 volts. And why 5 volts? Well, it's a nice round number that allows me to use reasonable resistor values. I'll try with 5 volts from bench power supply and the LEDs seem to be okay. Now I have replaced the PNP transistor and the NPN transistor. I also removed the 3 diodes and replaced them with 10 kilo ohm resistor. That makes this toggle circuit work even with lower voltages. I will use battery protection circuit when I pull the battery back. I'll test this with single 18650 battery that is sitting at maybe 3.7 volts. Now when I press the button, status LED toggles as it should. So I'd say the toggle section of the circuit is fixed. I took a look at the charging section. The IC used in this is actually single cell lithium charger, but there was a resistive voltage divider between the battery and battery voltage monitoring pin, which increased the charging voltage to 6.6 volts. I turned this back into single cell lithium charger, making this circuit match the one on the datasheet, but unfortunately that chip is dead. It just wouldn't start charging. This probably was the original problem which killed the battery. I will desolder all the charging components and figure some other way to charge the battery. But now it's time to try turn the LED on with the button. I previously tested the toggle circuit and LED module to be working, but now I have added boost converter to the toggle circuit's output and the LED module to the boost converter's 5 volt output. This should work with single cell battery. And yes, it works. Light turns on and off with the button. But now there's no charging circuit at all. I will do what many of us would do and use TP4056 module that also has the battery protection in it. I will connect this module to traces where the original circuit was, so the emergency function and the original charging port will work. I just need to use 5 volt power supply suitable for these TP4056 modules instead of the original power supply, which I don't actually even have. The original circuit had bicolor LED with common anode, which is actually pretty much the same configuration as on these TP4056 modules, so I can remove the SMD LEDs and wire those status pins to the original LEDs legs to make it work. Wiring is now done. Like I said, all the components from original charging circuit have been removed. Voltage from power supply comes through a diode on board and it's wired positive input of this module. Negative input is connected to ground on the board. In original port, the battery and charger grounds are connected together. Battery will be connected to B plus and B minus of this module. Module's positive output is connected to where the battery was originally connected. Output ground isn't required, as I said. The module's negative input and negative output are tied together, so are the grounds on the original PCB. I put thick heat shrink tubing over the module and tied it with zip tie, so it should stay in place. It took some work to put this LED here, with its legs going between all those new wires. I can start assembling this for a final test. I will use single 18650 cell for now, but I will make larger 1H6P pack later, when I get more cells. This should work just as well, but with shorter battery life and charging time. This is just temporary solution. Battery pack will be secured better before actually using this flashlight. This plastic divider should fit like it used to. There's space around unused bulb holder where I can actually place this boost converter. I'll make extra hole and use zip tie to hold it in place. Like so. I want to be careful handling this reflector part. I don't want to touch the main reflectors, so I don't ruin the chrome coating. There's no fixing it if the chrome wears off. There's key in the body, so this can only be placed on one orientation, and should click in place easily when it's positioned correctly, like that. And does this still work? Yes, perfectly. The flashlight is now fixed and I have put it back together. Hey, one function I haven't tested is the emergency function. If the light is on when the charger is connected, light should turn off, and if there's a power outage, the light should automatically turn on. But hold on, it doesn't work. We can find the reason in the schematic. After modification, the V in, the voltage from the power brick, is 5 volts. There's 10 kΩ from V in to base of the transistor and 1 kΩ pull down resistor. Those form a voltage divider and the voltage on the base pin doesn't reach required 0.7 volts. So if I replace this with, let's say, 3 kΩ resistor, it should work. I did replace the 10 kΩ resistor with 3 kΩ, and now emergency light function works as well. While this isn't the most modern searchlight, I think this is a decent light to have. I like the ergonomics and long battery life these larger flashlights provide. When I make that final battery pack with 6 cells in parallel, this should easily have about 20-hour battery life. See you next video. Thanks. Bye.